Everybody watch out, there's a wire over here. I've seen 6 people trip on it. So, all right. We're going to start again exactly where we left off with a little recap. What we've seen so far, MLPs can represent any function. They can be constructed to represent pretty much any kind of Boolean function, any classification boundary. They can approximate any continuous valued function as well to arbitrary precision, provided your network has sufficient capacity to model a function. The issue really was, given a function, how exactly do you construct a network to model it? And one way we sought to do it was, even if the network had sufficient architecture, we had to set the parameters of the network to model the function. And so one way to do it was to define the expected divergence, which is a measure of error between what the network actually produces and what you want it to produce, and estimate your parameters to minimize this expected divergence. The issue was that in order to compute the expected divergence, you need to know several things. You need to know the probability distribution of the data itself. You need to know the function that you're trying to model exactly. And both of these we do not normally know. So instead, we said we would sample the data. And provided the samples follow the distribution of the data itself, then you can expect that now the collection of input-output pairs, the pairs that you get as a result, somehow represent the function that you want. And so instead of trying to compute the expected divergence, you can compute the average divergence across your training points. And as we'll see in a later class, the average divergence is actually a perfectly unbiased estimate of the expected divergence. So you can sort of hope that if you minimize this guy over here, it will kind of minimize this term, at least in expectation. And then once we did that, we have now a function, which is the term to the right, which is our loss function, our empirical estimate of the expected divergence. And this loss function is what we were going to try to minimize. We were going to try to estimate the parameters W such that the loss is minimized. This was an instance of function minimization or optimization. We went through a crash course in function optimization. Where we left off was where we were talking about what we would do if you actually had functions of multivariate inputs, vectors. So now the derivative of a scalar function of a multivariate input x is a multiplicative factor that gives us the change in f for tiny variations in x. This is basically the same definition that we've always used for derivative. We saw this, right? So if I have any f equals f of x, right, y equals f of x, then delta y is going to be some derivative of f with respect to x times delta of x. And delta of x would be a column vector, so this guy is going to be a row vector, correct? And we also saw that in terms of definitions, you can define the gradient of the function at any point, which is simply the transpose, by definition, of the derivative when things are defined in this manner. So what exactly does this gradient mean? Now, again, if I write things in vector format, the derivative is a row vector, which is the transpose of the gradient, right? So if again, by definition of the derivative, what we are saying is df is the product of the derivative and the incremental change in x. So what is this term over here? We know dx is a vector. Dx is simply going to be something of this kind, right? dx1, dx2, dxt, right? So dx is a vector. This guy over here, this derivative 2, is a vector of partial derivatives. So the incremental change over here is basically an inner product of the derivative and dx, right? So what do we know about the inner product of two vectors? We know this, right? X dot y, for any two vectors x and y, x dot y equals magnitude of x, magnitude of y, cos theta, where theta is the angle between the two. Correct? So for any u and v, u transpose v is magnitude of v times magnitude of u times cos theta. So let's say I fix u and I fix the length of v. So this length is fixed. And then I rotate v around. At which point is this inner product going to be the maximum?
When they're pointing in the same direction.
When they're pointing in the same direction, when the angle is 0, right? Now let's go back to our derivative. We had delta y equals a gradient of f of x times delta x. So let me fix the length of delta x, and let me keep changing the angle of delta x. At which point is this inner product going to be maximum? Anyone?
In the direction of the gradient.
So when delta x points in the direction of the gradient is when this term is maximum, right? Can everybody see what I've written here? I'm assuming you can, yeah, right? If you cannot, let me know, right? So basically we have delta y equals the gradient of y with respect to x times delta x. This is a vector, this is a vector. If I fix the length of the step, so I'm always taking a step of the same length, I can take steps in different directions, right? The point at which this product is going to be maximum is when delta x is in the same direction as the gradient. So what does this tell me about the gradient? The gradient is the direction in which I must walk for the function for delta y to be largest. The gradient is the direction in which you must travel for the function to increase fastest. So basically, if the step dx is aligned with the gradient, that is when the angle between the two is 0, that's when the function increases fastest. So the gradient is the direction of the fastest increase in f of x. So for a function over here, this function increases in every direction. If you're here, you can take a step in pretty much any direction. Delta x, your dx could be in any direction, correct? But there is one direction where the function increases fastest. That's this guy. And so this direction is your gradient direction. Now there are two things over here. There's the direction of the gradient. There's the magnitude of the gradient. So the direction of the gradient is the direction in which you must walk for the fastest increase in the function. The magnitude of the gradient is how much the function is going to increase for a unit change in x, right? Okay, so that's the direction over here. If that's the gradients, moving in that direction increases f of x fastest. Moving in the exact opposite direction has the exact opposite consequence. F is going to decrease fastest, right? So that's the direction of the fastest decrease of x. And of course, anytime you get to a local minimum, a critical point, the gradient is going to be 0. Because basically what you're saying is that for infinitesimal, really, really small changes in x, the function isn't changing. That's what you mean by a minimum if the function is continuous and smooth, right? So there's another property of the gradient that we will frequently use. For any function, I can draw an equal value locus, meaning I can slice the function at any height. If I slice the function at any height, you're going to get these edges, which are the loci, equal value loci, and the gradient at any point is always going to be perpendicular to this equal value locus. It's something that's easily provable, but I won't go into it, okay? But this is something that we will use. And of course, we've all encountered the Hessian in your quiz. Now, so going back to our problem, finding the minimum of a scalar function of a multivariate input, like a loss, where the input is the set of all parameters of the neural network, requires the finding of a turning point where the gradient is 0. So if I want to perform unconstrained minimization of the function, what I can do is simply solve for this. If I have a function and I know the formula for the function, I can compute the gradient at any point. I can compute the gradient as a function of the variable x. And then I can solve for where gradient of f of x is 0. That's going to give me the set of all critical points. Furthermore, I can compute the Hessian at each of these critical points and pick the locations where the Hessian is positive definite or positive definite, semi-definite. And that's going to be a maximum, right? Or a minimum. The problem is closed form solutions are not always available. You're not going to be able to just say, suppose you have a function of this kind, a hideous function of this kind. You cannot simply, it has a unique minimum, right? But if you just try to solve for gradient of f of x equals 0, you're going to find that it's not easy to solve for it. It doesn't have a closed form solution. It may have a solution. It won't have a closed form solution. So in these cases, you're going to use an iterative solution. You begin with a guess for the optimal x and refine it iteratively till the correct value is obtained. So what you will do is start from an initial guess, x0. So you have some function. So you have x, f of x, and you have some function, and you're going to start off saying, I think my minimum is here. So this is my initial guess. But then when you get the minimum, you go and check the gradient. Will the gradient actually be 0? If you're not at the minimum, the gradient may not be 0, right? So in this case, what is the derivative slope going to be? Is it going to be positive or negative? It's going to be negative. Why? Because if I increase x, the function is decreasing, right? So in which now I must adjust my initial guess. What must I do? Must I move forward or backward? Forward, obviously, right? I must go in the direction of decreasing function. So we want to start at an initial guess, and you can check whether this is a minimum or not by checking the gradient and the derivative. And if it's not a minimum, then you can take a step in a direction where you think the function is decreasing, right? How will you take a step, and how big must the step be? Easy enough. You're going to use this logic. If at this point the derivative is negative, it means that going forward is going to decrease the function, right? So you will take a step in the positive direction. So if this is a function of x, you're going to say x is going to be x plus some delta x, where this is a positive number, right? On the other hand, if your current guess is out here, what you will find is that the slope is positive, right? So going forward increases the function, which means you must go back. And so you're going to say x is x minus delta x, right? So basically what you can do is a positive derivative means moving left, decreases error. A negative derivative means moving right, decreases error. So you can have this very simple logic which says that while the derivative of the function is not equal to 0, if the sign of the derivative is positive, take a step forward, take a step backward. And if the sign of the derivative is negative, take a step forward, right? I can compress both of these into one equation and write it like so, without a check. I can say this is the same as saying, right, if dy by dx is greater than, is less than 0 this, else this, right? So I can just say the x plus sine of dy over dx times delta x. These are the same statement, right? When the derivative is positive, then actually no, minus, right? So when the derivative is positive, I want to take a step back. When the derivative is negative, I want to take a step forward. So if the derivative is negative, the sign is going to be negative, negative, and negative will become positive. This term must always be positive clearly, and vice versa, right? So this is fine. Now, questions? We're going to keep using this logic. This logic is going to be the rest of the course, right? So if this doesn't make sense, then nothing else will make sense. But then I don't need to actually use the derivative, sign of the derivative. I can combine the sign of the derivative and the step size and just use the derivative itself and multiply the derivative by something else. And it's exactly the same equation. Nothing has changed. I've retained the sign, and the size, the length of delta x has been derived as a product of some other step size and the magnitude of the derivative. But it's basically the same equation as this guy, right? And so basically, this is your basic gradient descent rule. You're going to start off with an initial guess, and if the current guess for f of x is not the correct answer, if the derivative is not 0, you're going to take a step, and you're always going to be taking a step against the derivative. So if the derivative is negative, meaning if the function is increasing behind you, you're going to step forward. If the derivative is positive, if the function is increasing ahead of you, you're going to take a step backward, right? And you will continue to do this until the derivative. Now, when would you stop? When would you stop? Moving in either direction. The simple test is to check the derivative itself, right? So the derivative is going to be, okay, will the derivative always be 0 at the minimum? Can you give me a such case where the derivative is not going to be a 0 at the minimum? Yeah.
If you take the function of absolute value of x, the derivative at the minimum.
So assuming the function is differentiable and continuous, yes. So this is, if I have a function and the function is like this, but I'm only allowed to look for solutions in this range, then will the derivatives be 0 at the minimum? No. But where will the minimum be? At a boundary. Okay, so there are different things to test. A more reasonable thing to be testing is, as I keep taking my steps, does the function value change, as opposed to is the derivative 0? Right? Okay. So this is the gradient descent or the gradient ascent rule. To find a maximum, you're going to move in the direction of the gradient. So that was for scalar functions, right? But I can generalize this to vector functions. Again, in a vector function of a multivariate input, we know that the gradient is the descent of a direction of fastest increase of the function. So if I want to maximize the function, I'm going to walk in the direction of fastest increase. That's how I expect to get there quickest, right? If I want to minimize my function, I want to walk in the direction of maximum decrease. So in other words, I'm going to take a step in the direction of the gradient, which is the direction of maximum increase if I'm trying to maximize the function. I'm going to take a step against the direction of the gradient if I'm trying to minimize the function, right? And so this is the trivial gradient descent algorithm. You're going to initialize x, and then you can have multiple criteria. You can either check to see if the magnitude of the gradient has become sufficiently small, but that's not a sufficient criterion every time, as we saw, because if you have a situation like this, the gradient here can be fairly large and you've still hit a minimum. An alternate criterion is to check if your function decreases a lot as over subsequent iterations. And while this condition is not satisfied, you're always going to take some step size times the gradient. You're always going to take a step against the gradient to go towards the minimum. So the overall gradient descent algorithm is going to look like this, just for reference, okay? So we've looked at the general problem. Go get yourself a coffee. You're better off spending time outside class and grabbing a coffee than sleeping here, okay? So let's go back and look at our problem, right? You're given a step of training set of input-output pairs. You have a loss function they've defined. The loss function is the empirical average divergence or error over your entire training set, and you want to minimize this with respect to W. Now this is a function minimization. We've seen exactly how to do this. And so the problem set now, and this we can do using gradient descent, right? But just writing things in this manner is not sufficient. Everything has to be defined. This is math, right? So what are these input-output pairs? You must define this, right? You have to define what is this function f. This function is our neural network, but how exactly do you characterize it, right? And what are its parameters? What is this divergence, this error metric that we are actually minimizing in order to learn our function? So all of these things have to be defined. Now, first, let's look at what is f and what are its parameters w. This is the easiest bit. We've just spent several lectures looking at it. Our function is just a typical network. It's a directed graph, directed network with sets of inputs and outputs. We're going to assume no loops. We will now, here's some terminology, that confusing terminology that confused me when I was a kid. We speak of input units. There are no neurons at the input. The input units are your inputs. This is general terminology. The only neurons that you actually have are those in the hidden units and the output units. So the output that you really want is the output of this final set of neurons. Everything else in between is performing some partial computation that's feeding to the output. More often than not, you're not really interested in the outcomes of these partial computations. You're only interested in what eventually happens. So the guys in the middle who you're not interested in, they can be hidden from you. We're going to call them hidden neurons. Now, we're going to assume a layered network for simplicity, simply because it's easier to explain. This is not mandatory. Your network need not be layered. Pretty much all the logic we're going to talk about will still hold, except that writing everything in vector form becomes a little more tedious and sometimes impossible if things are not properly layered. So we will refer to the inputs as the input layer, no neurons here. The outputs are the output layer, and the intermediate layers are hidden layers, right? The individual, again, this is the network, but then we must define the individual neurons. And we're going to use the standard perceptron-like function that we've seen. I'm saying perceptron-like because the standard definition of the perceptron has a threshold function operating on an affine combination of the inputs. Here we are not going to be using a threshold function. We have some function f which operates on the affine combination of the inputs. So there are two different things happening over here. First, you have an affine combination of the inputs being computed. Second, that affine combination is going through a function. We are going to assume that that function is continuous and differentiable almost everywhere. I'm saying almost because if you have something like a ReLU, right, this function is not differentiable out here, right? But somewhere later in the lecture, you will see how to deal with these situations as well. So what are the parameters of this unit over here? The parameters of the individual neuron are the weights and the bias, right? And so the parameters of the entire network are going to be the weights and biases of the entire network. The activation functions themselves, we've seen threshold activations, but we're going to use something, other activations like the sigmoid, the tanh, the ReLU, and the soft plus. So again, these are just for reference. You have the activation functions and their derivatives on the slide, right? The key point is every one of them is differentiable, and you can actually compute the derivatives for every one of these guys everywhere except this ReLU. And then observe that the ReLU really doesn't have a derivative at 0, but the ReLU has something called a subgradient. Now, what was the derivative? If you think about it in terms of gradients, the gradient is the direction of the fastest increase of the function, right? So if I have a ReLU of this kind, at this point, what is the direction of the fastest increase of the function, right? What is the slope? So that's going to be, here the slope is defined. Here the slope is defined. At this point, we don't really define how much an incremental change in x is going to result in an increment in y. But you can sort of say that it's going to increase. So you can imagine pretty much any one of these lines as a reasonable approximation to what's happening at that corner. So we're going to call them subgradients, and the slopes of any of these functions will work just fine as the derivative at that corner. And typically we're going to use the best case, which is this guy. So the derivative at 0 will be defined as 1, right? Now, in all of these cases, we've assumed that the perceptron computes a single output, right? Or the neuron computes a single output. It computes a single affine combination of the inputs, and from that it produces a single output. But in a layer of neurons, you can have many such neurons, right? Now, there are other cases where instead of just producing a single output instead of having a single y, scalar y, as some function of x1 through xd, you can have a vector y as a function of x1 through xd. So basically in this case, you have a bunch of inputs going in and a bunch of inputs coming out. We're all familiar with such functions too, right? Your neural network is a classic case of a vector function. It takes a bunch of inputs, it produces a bunch of outputs. So you can actually have what we will call vector activations. We'll deal with these again in a little bit. But here's a classic example of a vector activation that we often use, the softmax. So you have many inputs and you have many outputs, but observe that you're computing a separate affine combination of the inputs for each output. Now, the actual output that you're computing is going to be this normalized exponentiation of the affine combinations. Now, what's special about this? What's different from a vector input, between a vector activation and just a collection of scalar activations? Now, to see this, you can see what's happening over here. If I have a collection of independent functions, right? Each of them is going through a sigmoid. This is one case. This is just a collection of sigmoid activations. In the other case, I have and these are going through a softmax, and I have a bunch of outputs. So as many outputs as these combinations that I'm computing, right? Now look at what happens here. If I change this weight, this is the only output that gets changed. The rest of the outputs do not get changed, right? So I can modify individual outputs without changing the other outputs. In a situation like this, if I change this weight, if I say modify this weight such that this value increases, the corresponding output over here is going to increase, but because all of the outputs are required to sum to 1, the rest of them are going to decrease, right? So changing any single parameter is going to change all of the outputs. So it's a fundamental difference between vector and scalar activations, except you can think of a collection of scalar activations as a degenerate case of a vector activation, right? You can have other kinds of vector activations like some crazy stuff. Anyway, so a typical network, in a layered network, you can actually view each layer of neurons, I keep calling them perceptrons, but they're really neurons, as a single vector activation. A degenerate case of a vector, in one case, if you have something like a softmax, it's a regular vector activation. In other cases where each neuron is operating individually on the inputs, then you can think of it as a degenerate case where modifying one output doesn't modify the other outputs, right? Let's introduce some notation. So I'm going to call, now every neuron has an input and an output, right? And there are weights. So if I consider the neurons between, say, the layer K This is the kth layer. I have many layers. I have several hidden layers, and I have a final output layer. I'm going to number the input as the 0th layer just to maintain consistency. So now the neurons of the jth neuron of the kth layer is going to have an output at each time in response to each input, right? I'm going to use the notation y j k to represent the jth output of the jth neuron in the kth layer. I'm going to represent the inputs as simply the output of the 0th layer, just so that I can use a common notation y across the board. But y0 simply means the inputs, right? And then if I have a connection between the, say, the ith neuron of the k-1th layer and the jth neuron of the kth layer, so this is the k-1, then I'm going to call this wij, which is to say connection from the ith neuron to the jth neuron, where the jth neuron belongs to the kth layer, the superscript k. So the superscript represents the destination layer. The second subscript represents the destination neuron. The first subscript represents the source neuron, right? So we've defined our network. We've defined the function. We've defined the parameters. We've defined a representation. But then how do we represent these input-output pairs? Now, the stuff that we were talking about when we began the course is, we said voice goes in and transcription comes out. That doesn't look like something you can represent as numbers, right? We want everything to be represented numerically. So the inputs, we're going to assume that the input is a d-dimensional vector, where the d components are real values. We're going to assume that the output is some L-dimensional output. So the nth input, you have a collection of training inputs. The first subscript represents to the index of the training input. You can have any number of these. The second subscript represents the components. So this means that your inputs are d-dimensional vectors with d components. Now, you have the target output, what you want the function to actually give you when you present this input, the desired output. So we're using the notation d to represent the desired output, right? And that's some L-dimensional desired output. The network will have a current output, y, which may not be the desired output, because remember, you're learning the network. And in any iterative algorithm, the current estimate of parameters is going to give you a network which is not the one that you really want, more often than not, right? So the output of the current network in response to the current input, we're going to represent using the variable y, which is basically the same variable that we used also to represent the intermediate variables, right? Now, the input itself is expected to be a vector of numbers, or it can be just a scalar if the input is of size 1. So if you're using images, the input could be a vector of pixel values. If you're trying to give speech as an input, the input could be just a collection of speech sample values or spectra, or some collection of features like spectra that you've derived from the speech using some external process. If you're going to be using text, then text is not real. So you're going to have to convert the text to some real valued vector in order to input it to the network. And we'll see how this can happen later, right? Or any other real vectors. Now the output, if the desired output is real valued, there's nothing to be done, right? That is really the function, that is really the output that you want the network to give you. But then if the output is, and in this case, if the desired output is a real scalar, then d is going to be a scalar value. If the desired output is a real vector, d is going to be a multi-component vector, right? It's a real vector, easy. Now, if the desired output is binary, like if you're performing a classification task, is the input inside the yellow region or not? Is the input image a cat or is it not a cat, right? So in that case, you have the output has two values, one of which represents one possible outcome, the other represents the other possible outcome. Like inside the pentagon and outside the pentagon is a cat, not a cat. We're going to convert these outcomes to numbers. So one of these numbers is going to be assigned the value 1, the other number is going to be assigned a value 0, And so now you have a numeric representation of the output. So now if I get some training instance of an image of a cat, then the target output is cat. I'm going to say the target output is 1. And I'm still building a cat classifier. Somebody gives me an image of a tree. The target output is cat. This is a tree. The tree is not a cat. So the target output is 0, right? So now if the desired output is binary, we can use a simple 1-0 representation of the desired output. The output activation in these cases is typically going to be a sigmoid, as we saw in the last class. And what the output of the sigmoid is going to be is really the probability that the output belongs to class 1 given the input. And this is what we will be learning, right? This indicates the fact that for actual data in general, a feature X may occur for both classes, but with different probabilities. And the nice thing about the sigmoid, of course, is that it's differentiable. If you have a multi-class input, then we will use something called one-hot representations. So let's say you're trying to build a 5-class classifier. Every input is either a dog or a cat or a camel or a hat or a flower, right? So now these are concepts. You have to convert them to numbers. So now because there are 5 possible outputs, we are going to use a 5-dimensional representation for the output. And the 5-dimensional representation consists of 5 binary values. Each one of the 5 is going to be either a 1 or a 0. And for a given output value, only one of these guys is going to be a 1. The rest will be 0. So basically, here you have 5 outputs, 5 possible outputs. So we will have a 5-component vector. And each component represents one of these labels. So the first component would be cat, the second would be dog, the third is camel, the fourth is hat, and the fifth is flower. So now if somebody gives me a picture of a cat, then I want to say, and so each of these 5 components is basically a yes, no for the 5 labels, right? So if somebody gives me a picture of a cat, I'm going to say the target output is 1 for the cat and 0 for everything else. If you get a dog, it's going to be 1 for the dog component and 0 for everything else. So observe that this vector has only one component, which is 1, and every other component is 0, which is why it's called one-hot. One of the components is hot, the rest of the components are not, right? So now for multi-class classifiers with n classes, the one-hot representations will have n binary outputs, which is basically an n-dimensional binary vector. Now, the ideal output of the network must be also one-hot, right? It must be able to see a picture of a cat and say this is a cat, in which case the output is going to be 1 for the cat neuron and 0 for the other neurons. In reality, what you will get is a probability vector. You're not going to get 4 zeros and a 5th 1. You're going to get 5 positive values, which together sum to 1. That's what the softmax gives you, right? This actually gives you the a posteriori probability of each of the 5 classes. Questions? No? Okay. So yeah.
What will happen if you don't have the softmax at the end?
So this is how we are setting up the problem, right? If you don't have the softmax, you're going to have real values, and you could choose a max, but the problem really is that you want something that's nice and clearly differentiable, right? Which is why we have the softmax, right? Yeah.
Could you use a normalization instead of a softmax? Like instead of exponentiating them and then normalizing them, you just exponentiate them?
If you just exponentiate them, they won't sum to 1.
No, as in not just exponentiate them, just normalize them.
So you remember that the outputs are going to be both positive and negative, right? There's no guarantee that the affine combinations are strictly positive.
But you can put a constraint.
You can do all kinds of things. I mean, you can design your neurons as you want, right? But there's the softmax is mathematically convenient and is congruent to probability. If you use something else, although it could very well satisfy the requirement that the highest value kind of indicates the label that you want, which is basically what we did when we used Adeline and Madeline, if you remember, right? It doesn't actually map onto a probability.
But normalization will also map on probability.
If you normalize it again, if you put a constraint, right, then if you actually map it, it's very unlikely that you're going to get a function which gives you this kind of curve, right? There's the nature of the curve itself, which represents how things really happen in life. So in a typical problem statement, you're given a number of training instances, say things like these, images of digits, along with information about which digit the image represents. So you can have tasks like, binary recognition. Is this a 2 or not? Multi-class recognition. Which digit is this? If you were doing binary, if you're trying to build a network to perform binary classification, then you would convert your training instances to something like this. The target output for each training input is now a grid of pixel values, so it's actually a numeric vector. And the target output is going to be either a 1 or a 0, right? If the problem here is to say whether the output is the number 2 or not. If you were performing a multi-class classification, then I've actually sort of used a lazy representation. The target output is now going to be 10 component, and it's actually going to be a 1-hot representation. So for the first image, the target output is going to be a 10 component 1-hot vector, where the 5th component will be 1 and the rest will be 0. For the second image, the second component would be 1 and the rest would be 0, and so on, right? So we've defined F, we've defined X, we've defined D, how to represent inputs and outputs. But we still have this issue of what this divergence can be. And we've seen that for the loss to be differentiable, the divergence must be differentiable. If the divergence is not differentiable, then you don't have a differentiable connection between the loss and the parameters. So you really want everything to be differentiable. You want the divergence to be differentiable, you want the function f to be differentiable. That's the only way you can find out how small changes in W are going to result in small changes in the loss, right? So the most common, the simplest divergence function that you can think of, again, the divergence is supposed to quantify the error between what the network actually produces and what you want it to produce. So the simplest divergence you can think of is the L2 divergence. You can just say, I have an output vector, I have a desired output vector, I can compute the squared Euclidean distance between the two. The reason you're using the squared Euclidean distance is again a matter of convenience. It's differentiable. If you look at magnitudes, then it's not differentiable everywhere, right? So the squared Euclidean distance is actually, observe that the way we define it, there's this scaling factor half outside. The scaling factor half outside is again just a matter of convenience. So then when you take the derivative, what you actually get is simply going to be a vector where every component is simply the actual difference between the target output and the actual output. So this vector is a vector of errors. And so originally when people described the gradient descent algorithm for learning neural networks, the error that the divergence function that they were thinking of was the L2 divergence. And in the L2 divergence, the derivative of the divergence is strictly the error, directly the error. And so they call the algorithm is called error backpropagation. The term error over there actually comes from the fact that when you're using an L2 divergence, the derivative is actually just the error, right? For binary classification, we like to use something else. Again, we like to think of the output as the posterior probability of the class. And this is where, again, the definitions begin to kick in, right? So it's easier to compute I can define any kind of a divergence between probability measures, the most common one being the Kullback-Leibler divergence. And the Kullback-Leibler divergence, anybody remember the formula? The divergence between two distributions? It's there's going to be summation I qi log of what? Pi over qi or qi over pi? Qi over pi, right? So p and q are the two distributions. In our case, the output y is going to be one distribution. The desired output d is going to be another distribution. So here, this really states what is the error I get when I assign this probability to the random variable, when the true probability is this guy. So this is the true probability. The term that's outside the log is the true probability. The term that's inside the log is the assigned probability. You want to match the two up, right? So in this case, what would the true probability be? This is going to be just the target, right? The one hot vector. And so you're going to get d times log of y plus 1 minus d times log of 1 minus y, where y is the output of the network, which goes between 0 and 1. So if I were to take the derivative, you get this interesting derivative, which is, observe this, it's minus of 1 over y. So if the desired output is 1, it's minus of, and it's 1 over 1 minus y if the desired output is 0. You can just work this arithmetic out. It's fairly trivial. But what happens when the desired output is 1 and you actually get a y that's 1? What's the derivative? Yeah. Anyone? So let's say the desired output is actually 1 and your y, your network is perfect. It actually computes an output y equals 1. What is the derivative here? 0? I have the formula here, right? It's minus 1, right? Similarly, if the desired output is 0 and the actual output is 0, what is the derivative? It's 1, right? In neither case is the derivative when you get the correct answer equal to 0. Just observe. Don't always expect the derivative to go to 0 when the answer, the network is actually correct, right? So this is, and why is this happening? Because you're restricting the output to lie between 0 and 1, right? So now if I have a multi-class classification problem, then once again I can use the Kullback-Leibler divergence between the actual target output, which is 1 hot, and the output produced by the network. And when I do this, I'm going to end up, rather than the Kullback-Leibler divergence, we can use the cross entropy. The two become strictly equivalent. So here is the divergence that we're going to use. It's minus summation d log y, right? So this basically, remember that this one of the basic properties of entropy, that if the probability distribution you assume is the same as the actual probability distribution, then the entropy is going to be, then this term is going to be minimized. Whereas if y is not equal to d, it's fairly trivial to prove that this term is going to be greater than, it's not going to be minimum, right? So now d is a one hot vector, right? So this is really going to be, let's write out the cross entropy KL divergence between a one hot vector and the output of the network. The KL divergence is going to be summation I di log of di over yi, right? Is going to be summation I di log di minus summation I di log yi. What is this term over here? Di summation di log di, given that only one of the d terms is 1 and all the other d terms is 0. What would this be? That's just going to be 0, correct? And so this goes away. You're just left with this term. But then it gets even more interesting. Only one of the d terms is 1, the rest of the d terms are 0. Right? So that's going to be, let's say dc equals 1 and di equals 0 for I not equal to c. Then you're going to get 0 times log y1 plus 0 times log y2, and then plus 1 times log yc plus 0 times log, basically all of these terms, all of the terms for the outputs not corresponding to the target class are multiplied by 0. The only term that is multiplied by a 1 is going to be this guy, right? So this ends up being a very, very simple formula. It's the negative of the log of the probability assigned to the correct class by the network. Everything else goes to 0. So although the formula looks fairly complicated, it collapses to something trivially simple. The divergence is simply the negative of the log of the probability assigned to the correct class. Now look at what happens over here. If the probability assigned to the correct class is 1, this term becomes 0, right? If the probability of the assigned to the correct class is 0, this term becomes plus infinity, right? Log of 0 is minus infinity. There's a minus outside. It becomes plus infinity. So as you go away from 1 for the correct class, this value increases very rapidly and becomes very large, right? And so this is why you want to minimize it, and it has this nice property. When you hit the correct answer, it actually becomes 0, right? And so if you take the derivative, now this is not a function of the probabilities of the wrong classes. So this is crazy. Although the formula itself includes all classes, when you actually collapse it, the only term that remained was the log of the probability of the correct class. So when you look at the derivative is going to have zeros everywhere except the one component that corresponds to the correct class, where it's going to be minus 1 over the probability assigned to that class by the network. Right? Questions? Okay. And so again, yeah.
I couldn't tell how the K divergence reduces to cross entropy here, because should there not be a diagonal at the bottom there?
So here's what this is. I should be a little more careful when I write this, right? It has to do with the fact that I have summation I di log di over yi equals summation I di log di minus summation I di log yi, right? And this term goes to 0. Because all of the terms, only one term, this log is slower than linear, right? So for all but one term, this guy is 0. For that one term for which this is 1, this is also 1, log of 1 is 0. So this is going to become 0.
But those are the probabilities, right?
No, those are the true probabilities, right? Which is the one-hot representation. Right? Remember, we said that when you write these terms, this guy here is the true probability of the data. This is what is assigned to it.
And one more thing, wasn't K divergence negative of that summation di log di 1, right?
No, it's summation log. It's a positive, so which is why it actually collapses to minus d log y. If you flip it, you will actually find that it becomes a negative number. Right? I mean, you can plug it in right there. Just look at what happens if I flip it. Even if I flip it, this term is going to be 0, correct? But what would happen when things match? That's going to become the worst case. Right? Yeah.
Why can't we use the squared error loss?
You could. It turns out that you actually can. Now, the issue with the squared error is that it's not going to give you this nice property where only one component remains. And if you actually plot the functions, I have plots for this somewhere. If you actually plot these functions, the KL divergence. So let's say you have some d is the true input, right? True value, and y is what you get. The KL divergence is going to have some shape which looks really bad, like so. It becomes very steep, and the quadratic is going to look something like that, which stops at the boundaries. So the shapes are different, and the KL divergence kind of pushes you towards away from really bad values very quickly, But then when you begin getting to the center, if you have non-binary target outputs, it turns out the KL divergence is not as good as just using the quadratic. So you can actually use different error divergence functions. This just happens to be something that we use because of mathematical convenience. Right? And the KL divergence works particularly well when the target outputs are binary, when you're at these junctions. So let's try plotting it, right? Maybe you can help me. I don't remember this very clearly. So let's say my target output is 0, and this is y. How is the divergence going to look? So when y is 0, what do I get? 1, right? And when y is 1, what do I get? Infinity, right? Or when y is 0, what do I get? When y is 0, the di is 0 and y is 0. So this is going to be, the error is going to be 0. And when y is 1, I have di is 0 and y is 1. So that's also going to become 0, right? What does it look like in between? Can anyone help me plot this? Yeah. So I'm trying to plot this. The target output is di is 0, right? Let's consider the case where I have a two-dimensional output, okay? So if I have a two-dimensional output, I have d is 1, 0, right? And y is going to be whatever, y1, y2. And the KL divergence is simply going to be minus log y1, correct? So when y is 1, and let's say when y is 1, what is the output? When y is 1, the output is 0, right? The error is 0, right? And when y is 0, it is infinity, plus infinity, right? And it's actually going to be, and the slope over here is already, what is the slope? It's going to be minus 1, right? So this divergence is going to look like that, really steep, right? Now if the desired output were the inverse, if the desired output was 0, it's going to look like that, really steep. And so you can see why this is actually a good divergence in this case, in that it actually pushes you towards the correct answer really quickly, right? If I were to use a quadratic divergence, what would it look like? It's going to be something like this, right? Not very nice. Make sense? Right? So, any more questions? Any questions about what I just explained? Must have gone over several people's heads. No, okay. All right. So, once again, observe that the derivative is not 0 when the answer is correct, right? Because of this property. This is what the derivative actually looks like. The derivative will continue to go down, but these are not valid answers, right? Okay. So, sometimes for multi-class classification, we like to do this other thing. We do something called label smoothing, where instead of using 1, 0, we might do something like 1 minus epsilon, epsilon, right? Or if I have many classes, I can do a 1 minus epsilon and then epsilon over k minus 1 for all the other guys. So why would I do that? The reason for this has to do with the derivative of the sigmoid again. You don't want the function, the sigmoid, to completely flatten out. So not the derivatives, the divergence itself. You want to have a non-zero divergence everywhere. And the sigmoid, if your function is 1, 0, then when you're far enough away, the divergence is going to become negligible, right? you can also write down the derivative over here. And you can see that the derivative for the components, incorrect components, is non-zero. Whereas if you actually had just the standard one-hot representation for your target, then the only thing that you're actually going to directly correct are the parameters for the correct class, and the others and the rest of them remain untouched, right? So we like to have this slight modification of the target labels using the smoothed labels, in which case you actually get a reasonable derivative for even the non-target classes. So here's the problem setup again. Yeah. Pardon me?
The labels missing
Uh-huh.
is known as one of the regularization.
Yeah.
But in this case, you mean that instead of prevent overfitting, the label is missing.
It really has to do with the fact the direct. I mean, you can use any terminology that you want, right? But to really understand what's going on, look at what's happening with the derivatives itself. If I give you a target output, right, which is maybe 10000, and I get some error. Now let's say, consider this. So let's say my target output is 10000, right? And the actual output I get is 0.01, point whatever, 1, 0.2, 0.3, 0.39, right? I have 4 horrible outputs. The only one that actually gets corrected, if I were using a one-hot representation, is this guy, right? You'd like to say the others must also get corrected. They're also bad. And the standard representation will not allow you to do that. Whereas here, you actually manage to get a derivative for those incompetent outputs and make a correction for them, right? So here's a problem setup. Finally, you're given a training set of input-output pairs. I don't even know how to shut my phone. Okay, you're given a training set of input-output pairs. You define an error on the ith output using this divergence. And then the loss is the average divergence across the entire training set. And this is what you're going to minimize with respect to all of your parameters, right? And we will use gradient descent to do this. This is the gradient descent formula that we saw. Now let's look at what happens. The gradient descent literally says that you're going to compute the gradient of the loss with respect to all of your parameters and then take a step against the gradient, right? Now, how many parameters do we have? We have many, many parameters. That vector x actually has many components. So you can look at it at a component level, right? And you can say that you want to compute, when you compute the gradient, you're computing the partial derivative with respect to every single component. So you're going to take a negative step against the derivative with respect to every single component. So from the neural network perspective, here's how we define our loss. We're going to initialize all of our parameters. I'm going to assume the bias is also a weight for convenience. And so literally for every layer, for every single ij combination, because weights go from a neuron I to neuron j, you're going to compute the derivative of the loss with respect to that weight and do the gradient descent update, right? Now this means we need to be able to compute this derivative. And now here's how we define the loss. The loss is the average divergence across all of your training samples. The averaging is a linear operator, which means that the derivative of the loss with respect to any weight is going to be the average derivative of the divergence with respect to the weight for across all of the training samples, which really means that what we really want to compute is this guy, the derivative of the divergence between the actual output of the network and the target output of the network with respect to each parameter for each input. And again, the divergence and this derivative are going to change with the input, right? So now, before we continue, here's a quick calculus refresher. I'm way behind today, so I may just have to record some of this lecture if I run out of time to do it in class. Just warning you, next week, right? Okay. So for any differentiable function y equals f of x with derivative dy over dx, we know that that property must hold. Delta y equals derivative times delta x, right? So for any differentiable function of many variables with partial derivatives, we also saw that this must hold, right? This was again the definition of the derivative. We've gone over this a few times. Now consider this guy. Let's say I have a function y equals f of g of x. So it's a nested function, right? What is the derivative of y with respect to x? So now this is actually a two-step process. So I can first define z equals g of x. If I say z equals g of x, then by our derivative rules, delta z equals dg over dz, or dg over dx, dz over dx times delta x, right? So this is just our derivative rule. And now y equals f of z, which means that delta y equals df over dz times delta z. This is again just our derivative rule, right? And I'm going to plug in this delta z from the first guy, which gives me df over dg times dg over dx, right? So you can see how this particular chain rule is directly derived from the basic definition of derivatives, right? So now I'm going to increase that one step further. Now let's say I have a function y, which is a function of many subfunctions. It's a nesting of many it's a nested function where there are several subfunctions. So y equals some function of g1, g2, g3, g4, g5, all of which are functions of x, okay? Now what is the derivative of y with respect to x? So again, let me, the slides are maybe a bit busy, so let me try to write this cleanly. And this, so I have y equals f of g1 of x, g2 of x, and so on, correct? So let me say zi equals gi of x. Then I can write y equals f of z1, z2, z3, and so on, correct? And we already know that in this case, delta y equals the partial derivative of y over z1 times delta z1 plus partial derivative of y over z2 times delta z2, and so on. This is what we've already seen, right? This is just a standard definition. But then I also know that delta zi equals dgi over dx times delta x, because z is just g of x, right? So combining the two together, I can say delta y equals the partial derivative of y with respect to g1 times partial derivative of g1 with respect to x times delta x plus y with respect to g2 times g2. These are not partials, these are complete, right? g2 with respect to x times delta x, and so on, right? Delta x is common across the lot, so I can group the entire lot, and I get this function, which is your well-known distributive law for derivatives, right? Now you have to get really comfortable with the notion of distributing derivatives. How exactly do you compute these? There's a very nice, convenient way of thinking about the whole thing, which you will encounter in your quiz, just to make sure it's burned into your mind, right? I can draw the entire dependency between x and y through what I will call an influence diagram, right? X influences g1, x influences z1 through g1, x influences z through g2, and so on. So x influences each of the z's through the corresponding g, and all of these z's finally influence y, right? So how does a small change in x, an incremental change in x, change y? An incremental change in x is going to result in an incremental change of each of these z's. The incremental change of any of these z's is going to change y. And we've already seen that that is additive, right? So basically you can actually say that small perturbations in x can cause small perturbations in each one of g1 through gm, each of which individually affects y, which is why. And so when you have many things influencing one function, we've seen that when you get close enough to a point, their contributions are cumulative, right, through the partials. And so the whole thing just ends up being an addition. So now, how to actually compute this derivative dy, derivative of divergence with respect to weight for a single input. Now first, let's take a closer look at the network itself. I've drawn a network for bivariate inputs, 2 component inputs. So the inputs have only 2 components, x1 and x2. I have a network. In fact, there's also a bias term. So I can actually expand out the actual computation in the network in this manner. At each neuron, you have 2 things happening. First, an affine combination of the inputs is being computed. Second, that affine combination is actually being put through an activation function, right? So when you do this, I can actually, so each of those yellow ellipses represents the totality of one neuron. And so now I can begin assigning labels to all the variables. So here are all of the weights properly, the arrows are properly labeled, right? And then you also have 2 things happening here, right? First, there's an affine combination, and then there's the actual output being computed. So we must label those as well. So first, I'm also going to label the affine combination of the inputs before the activation, and I'm going to label the output after the activation. So if I have the Z21 is the affine combination that goes into the second neuron of the first layer. Y21 is going to be the output of the second neuron of the first layer. Okay? So, and finally you have the output Y, from which you to which you also give the desired output D, and you compute a divergence, right? So now let's try to actually work out a little bit of how I would compute the divergence using the chain rule and everything else that we've seen for a couple of variables before we go on with the rest of the lecture in the next class, right? Spend a few minutes on this. So what is the derivative? The derivative of the divergence is, the divergence is differentiable. So let's assume I can compute this guy, which is the derivative of the divergence with respect to the output of the network. That's simply because the divergence is computable, right? It's differentiable, right? Now, what is the derivative of the divergence with respect to the affine combination that went into that neuron? Again, I'm assuming a single neuron, single output neuron, right? What would that be? That's simply going to be by chain rule, right? So that's going to be d div by dz. What is the label I've given it? Z13, right? Is going to be the derivative of the divergence with respect to y times the derivative of y with respect to, this is easy, right? Nothing particularly complicated. Now, I can take a step back and say, what is the derivative of the divergence with respect to these weights, the weights for the third layer? So then I can write those like so. But hang on, before I do this, there's something missing, right? I have happily written dy over dz13, right? But y is a function f of Z13, right? So when I'm computing this derivative, what am I actually computing? I'm computing the derivative of that function. Where am I computing the derivative? Remember, if I have any odd function, if I have a function, let's say, the derivative is different at each location, right? Here it's like so, here it's like so, here it's like so, here it's like so, here it's like so. At which of these locations am I computing the derivative? Pardon me? At Z13. So which means it's f prime of at Z13, which means I must have a value for Z13, right? If I don't know what Z13 is, I'm not computing a derivative. Similarly, I can keep working my way backwards, right? If I work my way backwards now, assuming I have a derivative with respect to Z13, I can compute the derivatives with respect to all of these weights. Because Z13 is just an affine combination of the previous inputs with the weights, it's kind of trivial, right? But then if I want to compute the derivatives further back, right? I want to compute the derivative with respect to, say, these weights, then I have to compute the derivative with respect to these y's, which is possible, right? I can apply the chain rule and take a step back. But then, from here, I need to compute the derivative with respect to this guy, which means I'm computing the derivative of this function at this location. Again, the z must be known, right? So you have this situation where the location at which you're computing the derivative must be known for you to compute the derivative, which means that you can't just start off computing your derivatives first. You need to compute the intermediate, the affine combinations for every single neuron in the network before you can begin computing the derivatives so that you can make your adjustments, right? So we'll see in the next class how the whole process happens, forward and back, right? I'll stop right here. Questions? Okay, thank you.